Dear students, in this video we are going to see about Hartley oscillator. It is a part of optics and electricity course. So first of all, we are going to see about what is a need of an oscillator. So here the oscillator circuit is capable of producing AC voltage of desired frequency and desired wave shape. To test the performance of electrical circuits, it is called as signal generators. It can produce square wave, pulse wave, triangular wave, and Sharp-tooth waves. Different shapes of waves are produced by an oscillator. High frequency oscillators are used in broadcasting. Here, microwave oven uses an oscillator, and these oscillators are used for induction heating and dielectric heating. The oscillator types are sinusoidal and non-sinusoidal oscillators. The oscillators generating square wave are a train of square waves is called as multivibrators. The multivibrators are divided into three types. One is bistable multivibrator. So the example is flip-flop circuit. Second one is monostable multivibrator. Third one is astable multivibrator. The astable multivibrator is called as free-running multivibrator. So here in oscillators, we are using the positive feedback. Depending upon the types of feedback, we have three types of oscillators. One is tuned circuit oscillators, RC oscillators, and crystal oscillators. So in oscillators, we are using that positive feedback. So the gain with positive feedback is given by the equation AF, that gain, that is called as the gain, is equal to A by 1 minus A beta. Here, beta is the feedback constant. So here, 1 minus A beta is equal to 0, or A beta is equal to 1. So that we are getting the gain equal to infinity. So this condition is known as Bergson criterion of oscillations. Here, by using these conditions, we conclude we are come into the conclusion that you may get output without any input. So how without any input, how some output is possible? So this is possible by using the circuit. So here this is that amplifier circuit, and the output of an amplifier, it is given to the feedback element, and it is the output of the feedback element is given as a input of that amplifier so that the output is given through the feedback element. So here the feedback voltage drives the amplifier. So here there are three possibilities are there. One is that when A beta is less than 1. So here we get decaying of damped oscillations. Damped oscillations means the amplitude of oscillations are decreasing gradually by increasing the time. So they are called as damped oscillators. So here the damping force is introduced in that oscillations. The damping force can be air or any other medium. The second condition is that if A beta is greater than 1, we are getting the growing of oscillations. This is that reversing of damped oscillations. The amplitude of waves are growing with respect to the time. The next one is that if A beta is equal to 1, we are getting that sustained oscillations. Sustained oscillations means the amplitude of that oscillation is not changing, it is a constant one. Here, in this circuit, supplies its own input signal so that without giving any input, we are getting some output here. So here in this, for an amplifier, where the starting voltage comes from. So here each resistor is a noise generator. The feedback network is a resonance circuit which is giving maximum feedback voltage of frequency F0 and it is providing a phase shift of 0 degree only at that frequency. Here, the initial loop gain A beta is greater than 1. So here the oscillations are building up only at this frequency. So here after the desired output is reached, A beta reduced to unity. Here we are using a tank circuit. So in this LC parallel circuit is called as the tank circuit. One that once the tank circuit is excited, it oscillates with a frequency. The frequency is 1 by 2 pi root of L into C. Here L is the inductance, C is the capacitance. So here that maximum frequency is calculated by using this formula. So this is that tank circuit. In this, one inductors and one capacitors are connected in parallel. There will be a switch is there. Once the switch is closed, the current passing through the capacitor. When this switch is closed means the current is passed through the inductor. So somewhat we are getting that excitation of the tank circuit while the current passes through it. And also this oscillating with the greater frequency. So these are that here that switch 2 is closed. The energy keeps on oscillating between the electrical potential energy and the magnetic field energy. Here, the magnetic field energy is produced by the current flowing through the inductors. So, by using the self-inductance phenomenon, when the current passing through the inductor, the magnetic flux is produced. So, due to which, by using this tank circuit, here we are getting damped oscillations. So, the damped oscillations here, that amplitude of the oscillation are decreasing gradually. So, this is the tuned collector circuit. So, in this will be a transistor. This is the NPN transistor. From that base end of the transistor, one capacitor is connected to the primary coil of the inductors. And the collector is connected with the capacitor and it is connected to the secondary coil of the inductors. So, in parallel to this, one capacitor is connected. This is acting as a tank circuit here. And the emitter is connected to that. So, here the emitter is Here the emitter is connected to that radio frequency oscillator and it is connected with that resistance parallel to that each other and it is connected to a voltage that is called as VCC. So here, the same circuit from the AC point of view is given here. So only the tank circuit is taken and it is connected to the transistor. We are getting that feedback element as the mutual inductance divided by the self inductance and that frequency due to that magnetic field induced there will be a flux will be produced so that tank circuit is oscillating with the maximum velocity, maximum frequency that is equal to 1 by 2 pi root of LC. This is the tuned trained oscillator. So this will be oscillator which is using a FET. Here also there will be a tank circuit is here. So here this will be that building of oscillations using that Hartley biasing. So here the damping oscillations are produced here. So next we move on to that Hartley oscillator. So before that we saw about that the basics of oscillations. So Hartley oscillator is a type of oscillator. This is using parallel inductance and capacitor element, which generates undamped sinusoidal oscillations. The tank circuit of Hartley oscillator consisting of two inductors and a capacitor. So in the tank circuit, two inductance coils are connected serially together and it forms a parallel combination with the capacitor. So this Hartley oscillator was first invented by Ralph Hartley in 1915. By his name only, it is called as a Hartley oscillator. So in normal inductance capacitance oscillators, the amplitude of the oscillations generated by the circuit is not controllable. But along with that, tuning of particular frequency is quite difficult for that LC oscillator. But for Hartley oscillator, Whittle uses LC parallel feedback configurations and it has self-tuning based oscillator circuit. This is the circuit diagram of Hartley oscillator. Here also we are using NPN transistor. The base of that transistor is connected to the capacitor and it is connected to the tank circuit. The tank circuit is consisting of two inductance and it is parallelly connected to a capacitance. The two inductances are connected serially with each other. Then that collector half transistor is connected to the radio frequency collector and it is connected to a voltage power supply. And from this collector end, one capacitance is connected and the output signal is taken from here. That emitter end is grounded by the circuit of resistance and capacitance are connected in parallel to each other with that collector end of the transistor. So by using this tank circuit here, that phase shift of oscillation occurred is 180-degree phase shift oscillations are produced. The output of this Hartley oscillator, it is like that, it is a sine wave. Then we move on to the working of Hartley oscillator. So here the record biasing of the circuit is provided by resistance R1, R2 and RE. Here that CC1 and CC2 are called as coupling oscillators and radio frequency component is present in the circuit. It is used to it is used for high frequency applications because the reactance of that radio frequency choke coil is very large so that it can be considered as open circuited. But in radio frequency choke coil exhibit almost zero reactance in the DC condition so that it do not cause any issue for DC capacitors so that the isolator maintains AC and DC conditions in the circuit. So by using that tank circuit in that output of that wave, we are getting that basic of 180-degree. This is provided by the transistor amplifier present in the circuit. The oscillating frequency relies on that components of tank circuit like L1, L2 and capacitance. When DC voltage is provided to the circuit, there will be a increase in the collector element of the transistor That capacitor in the tank circuit start charging. So here that capacitor store the charge in the form of the electric field so that that capacitor continues its charging until it is fully gets charges. But once it gets fully charged, the capacitor begins to discharge through the inductance coils L1 and L2. Here, the discharging of the capacitor results in charging of the inductance. The inductance stores the charge in the form of the magnetic field so that the complete discharging of the capacitor will automatically cause the charging of the inductance and vice versa, so that the continuous charging and discharging will provide the sinusoidal oscillations at the output end, so that the oscillations are called as damped oscillations. In the damped oscillations, the amplitude is decreasing continuously. So here, the decrease in amplitude is a result of internal resistance of the inductor. So this will be caused by the heat loss in that circuit. It is denoted by the Joule-Thomson heating law that heat loss is equal to I squared R. So it is noted that between the point of A and B in the circuit, a phase shift of 180 degree is provided by the tank circuit. As the point C is grounded, thus the particular time instant when A is positive, B will be negative with respect to C, so that the tank circuit provides a phase shift of 180 degree. Here, the tank circuit generates some damped sinusoidal oscillations. So the record oscillations are amplified, otherwise that oscillations will die out after a certain point of time. To overcome this problem, the output of the tank circuit is provided as input to the common emitter configuration of the transistor. The sinusoidal signal then provided to the transistor and the signal have to be amplified. The feedback energy is taken by the inductance of the coils between L1 and L2. Here, the amplified output is taken from the transistor and it provides the charging of energy to the capacitor in the tank circuit, and it further produces that sinusoidal oscillations. The amplified output compensate for losses generated by the tank circuit. That losses may be heat losses. Thus, the tank circuit provides continuous sinusoidal oscillations of constant amplitude at the output end. Likewise, the tank circuit in the Hartley oscillator is working. Here, the frequency of oscillations are expressed by the sinusoidal signal generated by the tank circuit. Here, the frequency of oscillations f is equal to 1 by 2 by root of L into C. L is the inductance of the coil, C is the capacitance. But in Hartley oscillator, we are using two inductors. They are connected in series and it is connected to a capacitor in parallel manner. So these inductors in the tank circuit provides the equivalent inductance. It is given as L equivalent is equal to L1 plus L2. So here the frequency of oscillations can be calculated by the mutual inductance between the coils. So, for calculating the equivalent inductance, we are using that mutual inductance between the two coils. So, here, once the current is passing through the one circuit primary coil, the EMF is produced in that secondary coil so that it is called as mutual inductance. So here the mutual inductance is denoted by that letter M. Here that equivalent inductance is given by L1 plus L2 plus 2M. M is the mutual inductance between the primary and the secondary coil. So that due to the mutual inductance, so that coil is oscillating with the frequency F is equal to 1 by 2 by root of LC. Then we move on to the advantages of Hartley oscillator. The Hartley oscillator provides sinusoidal oscillations of constant amplitude. That amplitude of oscillations are controlled by the inductance in that Hartley oscillators. So here that frequency of oscillations can be changed by the use of the variable capacitor used in that Hartley oscillator. The circuit of Hartley oscillator is not a complex one. Practically, there will be a single tap coil that can be also used in the place of two inductors in the circuit. The disadvantages of Hartley oscillators includes that due to the presence of harmonics, sometimes deserted sinusoidal oscillations are generated. So due to the harmonics means this is due to the frequency equivalence between the inductors and the capacitors. So here it does not find using low frequency applications. These type of Hartley oscillators are used in high frequency applications only. Then applications of Hartley oscillators. The Hartley oscillators are widely used in the generation of sinusoidal waveforms of certain frequency. So, these Hartley oscillators are suitable for radio frequency applications and they find their use in radio receivers. So that the Hartley oscillators are very much useful in that high frequency oscillations. So these are some points about Hartley oscillators. These Hartley oscillators are used in many radio frequency applications. So in this we saw about that types of oscillations, how that oscillations are produced in that Hartley oscillators and how that oscillations are generators and also how in oscillators positive feedback is inserted. So everything is included in that Hartley oscillator. So in this, that circuit of Hartley oscillators are very important. So we will first see how to draw that circuit of that Hartley oscillators. In Hartley oscillators, we are using the tank circuit. It consisting of two inductance and one capacitor. The inductance are connected parallel to connected seriously and it is connected to a capacitance in a parallel manner. So that here when the current is passing through that tank circuit due to which the tank circuit is oscillating. So it is oscillating with a frequency x equal to 1 by 2 by root of L into C. So here we are using two inductance coil so that we can calculate that inductance L is equal to L1 plus L2 plus 2M. So here that mutual inductance have to be added. So the mutual inductance means so when the current is passing through the primary coil, so there will be a magnetic flux is induced in that secondary coil. So that is called as that mutual inductance. So here that L equivalent can be calculated as L equivalent is equal to L1 plus L2 plus 2M. M is the mutual inductance. So here I share that window to draw that diagram of Hartley oscillator. So here I share that. So here I shared the window to explain that drawing of Hartley oscillator. So here the Hartley oscillator is drawn now. So first of all, we have to draw a transistor. This is the NPN transistor. So that arrow mark is outside. So it is called as NPN transistor. So with this, it is connected to the resistance and capacitance parallel circuit. And it is grounded. From that collector end, it is connected to the capacitor. From that, the output is taken out. So this is the output. So if from here, the tank circuit have to be drawn. This is the tank circuit. So this is here one inductance is introduced. Another inductance is here. So both this is L1 and this is L2, and with this it is grounded. This is the tank circuit here, and this tank circuit is connected to the base of the transistor by using the capacitor, and with that collector end, it is connected to a radio frequency choke. This will be the radio frequency choke. From this, the input signal is given for the positive end of the input. And from here, there are two resistance are introduced. They are connecting in that series manner, and it will be grounded. So here, this will be the circuit of Hartley oscillator. This is the tank circuit. So here, this will be the transistor. So here, that output is taken as a sinusoidal wave. So it will be like this. This is the sinusoidal wave. It is got as a output from the Hartley oscillator. So here this will be known as CC2 and this is CC1. This is RFC, radio frequency choke. This is R1, this is R1 and this is R2. So here this will be that load element. So load resistance, this will be the load resistance. This will be the load capacitance. So this is the capacitance. So here we are getting the tank circuit has added the further phase shift of 180-degree. Phase shift is added by using that Hartley oscillator. So this is that circuit of Hartley oscillator. So here by using this uh, Hartley oscillator, we are getting that maximum frequency when the current is flowing through the tank circuit, it is oscillating. The frequency of oscillation is defined as F is equal to 1 by 2 pi root of L by C. So this is the L equivalent because here two inductance are used. Here L is equal to L1 plus L2 plus 2M. Here M is the mutual inductance of that coil. So of that tank circuit. This is the mutual inductance. So here that Hartley oscillators is used for that high frequency oscillations only. So it is very useful for that high frequency oscillations. So but for that other things, other oscillators are used in that different low frequency oscillators. So here that inductance and capacitance are connected in parallel, that is used to determine the frequency. So here that feedback is added for oscillation is taken from that coil. This is the tank circuit. It is the here two coils are introduced. These coils are used to give that feedback for oscillations. So these are that some points about Hartley oscillators. So here that Hartley oscillators are very much useful, and this will be yeah, small circuit. This is not a complex circuit, very little and small components are used here. So this will be very useful for producing the oscillations for high frequency. So here the phase shift introduced by the tank circuit is 180-degree. There are some series fed Hartley oscillators are available. So here these oscillators are used for that same purpose only. By using this, we can adjust that frequency of oscillations by using that variable capacitors. The variable capacitors range is in between 100 picofarads to the 500 picofarad. So here, by using this Hartley oscillator, we are getting that upper frequency is in the range of 503 kilohertz. 503 kilohertz, up to which we can get that higher frequency by using that Hartley oscillator. The low frequency is this will be the high frequency FH. We can denote it as FH. the lower frequency. So that will be FL is equal to 225 kilohertz. So by using this, we can find out that bandwidth of that Hartley oscillator. The bandwidth is equal to, this is equal to high frequency of the oscillator minus low frequency. So this will be 503 minus 225. So we are getting the value as 228 kilohertz. So this will be the bandwidth of Hartley oscillator. So by using op-amp also, that is operational amplifier, we can produce that Hartley oscillators. And also bijunction transistors also used for that, and also FET also used for instead of transistors to produce that Hartley oscillators. That Hartley oscillators, so here, this Hartley oscillators, in this, instead of two inductance, two capacitors is added and it is connected parallel to that inductance. This will called as the Colpit oscillators. So this circuit is acting as a tank circuit in that Colpit oscillators. So here the output of the transistors emitter is always in phase with the output of the collector, so that the feedback signal is always positive in case of that Hartley oscillator. The oscillating frequency, which is a sine wave voltage, that is determined by the resonance frequency of that tank circuit. So these are that some points about Hartley oscillators, their construction and working is explained here.